So today we're going to be going over the Schrodinger equation and explaining what it means and how we can get the quantum numbers for the hydrogen atom from there. We are not going to do a full derivation or anything like that, but just to get a basic idea, where these things actually come from. So you can always just solve these things on your own if you're really motivated. All right, so we're going to be looking at the Schrodinger equation, and this is going to be the time-independent one. Now, when I mean time independent, this is what they call stationary states. In other words, this is your stable configuration. It's not going to change as a function of time. Now, we could look at the time dependent version, but all that does is basically just add a exponential time dependence onto the equation, and we really don't get anything more from there. But if we're just looking at a state that it exists, that's going to be the time independent version. So that's what we're going to be looking at. All right, so there is our time-independent Schrodinger equation. It is deceptively simple. So we're just going to explain what each of these little symbols actually mean here. All right, so first up we have the H, which represents the Hamiltonian operator. And the Hamiltonian in physics is what represents the kinetic energy plus the potential energy. All right, and this is an operator, meaning that it's going to be some type of mathematical function that will give us the kinetic energy plus the potential energy. All right, the E just represents the total energy, and this is going to be a scalar quantity. In other words, it is just a number. All right, so this Hamiltonian is kinetic plus potential. Remember, that is our total energy, but this is going to be some kind of a mathematical function. The actual total energy itself is just going to be a number. And then finally over here we have the psi, which is the wave function, and this contains all the information about the particle. And this, of course, is going to be showing us what our orbitals and everything actually look like. So right here, the psi, this is our most interesting thing. And the psi on both sides are obviously the same. So essentially what we're doing is we're taking this mathematical Hamiltonian operator, operating it on this wave function, and when we do that, assuming that the Hamiltonian is correct, the wave function is correct and everything, we're going to get over here the energy multiplied by that original wave function. All right. Now, how does that actually work? So it's a fairly simple example. We can look at the following equation. All right, so we have the following mathematical function. The second derivative of the sine is equal, of course, to the negative sine of x. So if you remember, the first root of the sine, of course, is the cosine. You take derivative again, you get the negative sine. So essentially what we have here is that this part right here would represent our h. This would represent my wave function. This little negative sign right there represents my energy. And again, this part over here represents my wave function. So essentially what we've done is take this mathematical operator, the second derivative, operated that on the wave function, which is the sine of x, and we've got back the negative of this original wave function. So the e right here would just be a negative 1. All right, and this is what is more generally termed an eigenvalue equation. And you'll see these all the times. These happens all the way in calculus and linear algebra. So these are very common mathematical formulations here. All right, now of course this doesn't work on any general function. I mean, if I put in here the second derivative of x cubed, obviously I wouldn't get back some scalar times x cubed. So only certain functions are going to work, and of course those are going to be the solutions for a particular wave function here. All right, actually we're going to be seeing here in a little bit that the second derivative actually does show up in the Hamiltonian itself as the part of the kinetic energy operator. All right, then as for the wave function, what does this actually mean? What does it actually do? And we'll just talk about this a little bit. All right, now for the wave function here, we cannot measure this directly. The wave function many times is going to be a complex number, meaning that there's going to be real and imaginary parts to it. So because this wave function over here is going to be complex, it's essentially going to be something like a plus ib, right? So your real number a plus your imaginary number, which is of course is the square root of -1, just to remind ourselves. So I, that's equal to the square root of -1 times b. So this is, what the wave function is generally going to be some kind of a function of. Now, what we can measure is actually going to be the wave function squared. Now, because of course this has imaginary components to it, there's no way we can go to a wave function meter and actually measure the actual wave function. What we can do is take mathematical operators, operate on that wave function, and get out real numbers, and then those real numbers will tell us some of the properties of the particular wave functions, like momentum and position, energy, those kind of things we can pull out of the wave function. So this wave function, we can't measure it directly, even though it does contain all the information about the particle. So all the information's in there, but we can't get it all at the same time. So what's going to happen is that if we take the wave function and multiply it by its complex conjugate, that's what this little star up here represents, the complex conjugate of that. This is going to be real, and also we can also say real and greater than 0. So it's going to be a positive number greater than greater than or equal to 0. So it could be equal to 0 as well. It is going to be a pure real number. And this psi squared is going to basically be your probability. And just to explain, how this actually works, just in case it's been a while since you've done with complex numbers, this would be a minus IB times a plus IB. And that's just going to equal a squared plus b squared. All right, and of course that's going to be greater than or equal to 0 for all numbers that you can deal with. Now, what does the actual equation look like if we're dealing with hydrogen? So what we have here for hydrogen is this equation, a little deceptively simple. So we have here a whole bunch of variables, and we're not going to go through all this. H bar squared, remember that's Planck's constant divided by 2 pi, which is h bar, so we know that. The mu right here, just point this out, the mu, this is your reduced mass. So really 1 over mu is equal to 1 over the mass of the electron plus 1 over the mass of the proton. And essentially you just solve for the mu, and that's going to give you reduced mass. That's essentially what you have to do if you're dealing with a two-body system and you want to put this into the center of mass coordinates. So the reduced mass is going to be approximately equal to the electron mass. There's just this little minor correction because the mass of the proton is finite. Over here, the del squared, this is what is called the Laplacian. And this is equal to... So you may have seen that. Basically, this is just a little shorthand for this one. And this is going to be in Cartesian coordinates. And if we're dealing with an atom, we have, of course, the electron going around in a spherically symmetric field, around the proton. So Cartesian coordinates are not the natural coordinate system for an atom. Instead, we want to be using spherical coordinates. So in reality, we wouldn't be using this. We'd be using the, the variety of the Laplacian converted into spherical coordinates. I'm just going to display this on screen and not try to write it out right now because I will probably goof this up. But essentially that would be the version that you would be using. They're essentially identical. So you're now using more natural coordinates, the distance from the proton as well as essentially the latitude and longitude of the electron there. So that would be your theta and your phi. And by the way, this little symbol right here, when you're pronouncing this, this would be pronounced either del. Okay, so that's usually what they just say, del square, that's what they're referring to. Although the actual symbol right here is actually called a, what's called a nabla. All right, and nabla, that's actually this kind of a Hebrew harp thing. It looks like an upside down triangle, apparently. So that's where the name basically comes from there. The other thing here, the E that we see, this is going to be your electron charge. 4 in pi, we know that. The epsilon 0 is called the permittivity of free space. Essentially, that's just your conversion factor between coulombs and your forces and newtons and joules and everything like that. So it's essentially just your conversion factor along with the 4 pi. And here R, that's just going to be your radius, your radial distance, which is, if we're dealing with this in x, y, and z, would be your square root x squared plus y squared plus z squared. And then here your energy, of course, is just going to be your energy levels. And actually, one thing about this Schrodinger equation is that there's not just one wave function that you can actually solve for. There's actually many, many, many wave functions, and they each have their own energy levels. And of course, this is when we start looking at the energy levels in the hydrogen atom, is that it's not just one energy level, one wave function. We have multiple wave functions over multiple orbitals and multiple energy levels, and they're all going to be solutions to this. So essentially, we're not just finding one solution, we're finding a whole set of solutions. All right, and remember I said that we're finding a whole set of solutions here. Now, what we basically have here is that all these wave functions are going to be orthogonal. All right, now orthogonal is just a fancy term for being perpendicular to one another. Now, perpendicular, of course, usually just refers to, like, right here, these two lines. You know, this is perpendicular to that one, approximately. But we're talking about being orthogonal. This is just a more generalized version of being perpendicular. So, for instance, if I were to have here a little graph, so here's my x and here's my y. Well, if I were to have a little point right over here at point A and B, well, this is just going to be ax plus by. Now, x and y are orthogonal to each other, meaning that there's nothing I can do, there's no number I can multiply x by to turn it into y. I need to have both of these x and y components to describe this point. If I just have one, there's no way I can, get up there, right? There's no, x I can multiply some number by x to get it up to here, because you're just going to be stuck on the number line. So you're going to need the x and the y to fully describe this. Just like if you're dealing with the wave functions, to fully describe a particular wave function, you're going to need to add up your different wave functions to make a total solution here. Now, mathematically, how we can actually represent this as for the orthogonality condition would be right here. Okay, so very simply we can just write this, which essentially is saying that if you have two wave functions and you're integrating them over all space, they're going to be equal to, this is called the Kronecker delta symbol over here, and this little Kronecker delta here is going to be equal to 1 if I is equal to j, and 0 if I is not equal to j. Okay, and that's called your Kronecker delta. So essentially, if you have the same wave function and you're integrating over all space, you'll just get 1. But if you have a different wave function integrating over all space, you'll get 0. And that's only if these things are orthogonal. If they're not orthogonal, then this wouldn't actually hold. And the reason that this is so very important right here is that if I'm taking a generalized wave function, and I want to make up some generalized wave function here, so basically some generalized one, you can take all these different wave functions, add them up. Right? So you're basically summing up all of your wave functions from n equals 1 to infinity of these. So this is going to be all of your orthogonal wave functions, and essentially what they call a basis set of wave functions, multiplied by some number, of course your constants, that would be like your a and your b that we have here, and you just add up all these things, and then you can get your generalized wave function. So essentially you're taking your orthogonal wave functions, right, your x and your y, your z, your t, whatever, and you're just adding them up and to get your generalized wave function that can be described any point here. Now, where does this come in very handy is if you remember hybrid orbitals, right? So of course our hybrid orbitals, if we have here our sp orbitals, sp2, sp3, sp3d, right? These are the hybrid orbitals, and essentially to get these hybrid orbitals, we're going to be adding up our basis functions with the s orbitals, our p orbitals, and our d orbitals, adding them up with the appropriate weighting constants, the a sub n's here, to get these particular orbitals. And that's what why these wave functions are so very important. So all these orthogonal wave functions, these are solutions to the Schrodinger equation, and essentially if we just add up those solutions with the appropriate weighting constants, we can end up with generalized wave functions, which we can use as hybrid orbitals right here. Okay? So here is the generalized solutions for the hydrogen atom. It is a very complicated wave function. I'm not going to try to attempt to explain all the little symbols in here, but essentially what we can do is plug in for some of the lower values that we'd be interested in, like between 0 and 3 or whatever, and we can find out some of the solutions for the hydrogen atom. And we can also look at some of the principal quantum numbers that actually are used to describe this stuff here. All right, so there are 4 basic quantum numbers. We're going to start off with the first 3, and these first 3 come from the Schrodinger equation, and this is the n, which is the principal quantum number, the L, which is the angular momentum quantum number, and the m, which would be the m sub L, which would be our magnetic quantum number here. So n is your principal quantum number, and this goes from 1 all the way up to infinity. Now, obviously, it's not going to have all those values, but it can take on any value between 1 and infinity for those. And essentially, this is going to be describing your energy level, which also is your shell, and essentially the distance from the nucleus. All right, the next one we have here is going to be L, which is your angular momentum quantum number. Now, the L here can take on values from 0 all the way up to n minus 1. All right, so essentially the n is the first thing you're going to know, and then you're going to move on to the next one, which is going to be the L, and then, as we're going to see later, the m sub L. All right, now these values here are going to describe the shape. So this is going to describe the shape. Also, it will describe, obviously, the angular momentum of the particle, but we're really not going to worry too much about that for our purposes here. Now, as for the shape, we're going to have here the s, p, d, and f orbitals. So if we're dealing with, put this over here. So for L equals, this is going to be our letter, the S, P, and now why are these called S, P, D, and F? It's for historical reasons. When they were doing spectroscopy, they were looking at many lines, and they needed some way to describe them because some of them were broader, some were narrow, some were very weak. So they used some terminology to describe them, so when somebody else was looking at them, they could know what they were actually looking at and if the lines were coming from a similar element or there was something else actually going on. So one of the ways that they were used to describe them was called sharp, principal, diffuse, and fundamental. And essentially, when they started naming the orbitals, the letters nomenclature basically just stuck. So it's basically just for historical reasons. Now, even though these things are called sharp, principal, diffuse, and fundamental, and you may say, well, does that mean that transitions from or to these orbitals have certain characteristics of, being sharp or diffuse? No. It's, again, just for historical reasons, transitions to and from these orbitals. So we can't say with any certainty, how the actual transitions will look just because they happen to be coming from these particular levels. So there's no correlation between, the SPD and F and, actually being, this kind of a description of the lines. It's just purely for historical reasons. All right, and then the final one here is the M sub L. And this is your magnetic quantum number. And this is going to be integers between plus and minus L. Basically, we start off with the n, we get those values, then we know exactly how far up the L can go, and then at the end we can get these values here, which are going to go between plus or minus L. And this includes 0 as well. And the magnetic quantum number here basically describes the orientation in space. When we're talking about orientation in space, it really doesn't make any difference unless you're applying some kind of an external electric or magnetic field. Because if there is no imposed coordinate system by an external field, the atom doesn't know, where your x, y, and z axes actually are. So the only time that you can actually start measuring and noticing differences between the M sub L's is if you put your atom into an external field. But if there is no external field, all the M sub L values, they're all going to be degenerate, and there's no real difference between them. And then the other thing which we'll be talking about a little bit is the M sub S, and this is going to be your spin quantum number. All right, and this is going to have values of either plus 1/2 or minus 1/2. In reality, it's plus or minus h bar over 2, but this generally just gets simplified to plus or minus 1/2, just for simplicity. Now, this, and we're going to go a little bit into the whole Stern-Gerlach experiment and everything, but this does not come from the Schrodinger equation. All right, so the spin quantum number here actually comes from the Dirac equation. In the Dirac equation, I'm not going to write this down. It's more confusing than it needs to be. But essentially what happens is we take the Schrodinger equation and put special relativity into it. All right. So the Schrodinger equation that we started off with over here does not contain any stuff with special relativity. And remember, special relativity is what you have to do when things go fast and your reference frames and everything. Well, it's not included in this equation at all. But if you do include special relativity into the Schrodinger equation, you get what's known as the Dirac equation, and if you solve that, spin comes out of there naturally. Now, it actually comes out kind of in a weird sense because it involves matrices, but it does come out from the equation quite naturally from there. The other thing is the Dirac equation also predicted the existence of antiparticles. So at the time, nobody knew about the existence of antiprotons or positrons or any type of antimatter. But when you actually solve the Schrodinger equation, essentially you're solving for the wave function and you wind up with a square root in there. And if you remember, if you're dealing with your square root, essentially it's like if you're taking the square root of 4, the possible solutions are +2 and -2. Well, the negative solution wind up to be the antiparticles, and a couple of years after Dirac predicted the existence of a oppositely charged electron, they found the existence of positrons, which are just oppositely charged electrons. So that was another pretty great prediction from this equation here. Now, as for how do these things actually arrange themselves? Well, we'll go through and just make up a nice little table here, which will hopefully explain these, and it's really not that hard, but it just takes a little bit of practice to see that. So here we're going to have our principal quantum number, our angular momentum quantum number, are the letter that we're actually going to have for that, the magnetic quantum number, the number of suborbitals that we have, and the number of electrons that we can hold in this entire thing here. So just starting off for the first one, for n equals 1. Well, there's only one possibility for that because this can go between 0 to n minus 1, and n minus 1 is just 0. So there's just going to be one possibility, which is going to be your L. The letter that we're going to have there is just going to be an S. Okay, that's all we have. The m sub L goes between plus and minus L in this case. So that is just going to be plus or minus 0, just 0. Number of suborbitals. So that's the number of m sub L's that we actually have. So we just have 1 here. So that's going to be 1. And now each suborbital can carry a total of 2 electrons. Right? So this is going to be 2 electrons right there. Right? And that's all we have for the n equals 1 level. All right, next up for the n equals 2 level, the L values, again, this goes between 0 to n minus 1. So that's going to be 0 to 1. The letters that we can have are going to be our S and our P. The m sub L's for the 0 is just going to be 0 again. And for the P, that's going to be number of suborbitals. There's just 1 here. There's going to be 1. And here we have 1, 2, 3. And the number of electrons we have in each is going to be 2 over here. And now we have 3 of them. Each can hold 2 electrons. So we're going to have 6. And that's it for that level. Now for n equals 3, our levels can go 0, 1, and 2. The letters we're going to have are SPD. And the m sub L's, same thing like we had up here. And then for the D is going to go between plus and minus 2. Number of suborbitals, 1, 3. And here we have 1, 2, 3, 4, 5. And then again, just doubling these. All right, then we can go up here to our n equals 4. All right, and then for the S, P, and D, these are exactly the same for my m sub L's over here. And now for the F, that's going to be between plus and minus 3. My number of suborbitals, same thing here, 1, 3, 5. And now this is going to have 7, right? 1, 2, 3, 4, 5, 6, 7. All right, you should hopefully know the pattern right now. We're going in odd numbers, 1, 3, 5, 7, right? The odd numbers there. And then my number of electrons we have is just going to double these. And now 4. And the other thing you may just notice here is the total number of electrons for every n level here. So this is obviously just going to be 2. We combine these 2, that's going to be 8. Combine these 3 here, it's going to be 18. Combine these over here, that's going to be 32. What you also notice is, based upon my n, all these are going to go as 2n squared, right? 4 squared, that's 16, times 2 is 32. 3 squared times 3 squared is 9, times 2 is 18. 2 squared is 4, times 2 is 8. 1 squared is 1, times 2 is 2. Right. And it's actually another little fun thing. If you ever notice this, the sum of the odd integers is equal to the squares, right? 1 is obviously just 1. 1 plus 3, that's 4. 1 plus 3 plus 5, that's now going to be 9. Add another 7, that's 16. Add 9, that's 25. Add another 11, you get 36. Add 13, you get 49, and so on and so on. So you basically get the squares if you just add up all of the odd integers from there. So it's a fun little math fact for you. All right, now as for our final little property, which is the spin of the particles, we just need to explain what spin actually is. Okay, so spin is an intrinsic property of elementary particles. All right, and just like charge or color or mass, it's just the thing that the particle has. basically your intrinsic angular momentum of the particle itself. And it just is the way the particle is. And like I said, the spin, this came about when you use the Dirac equation in there. Because of this spin, as we can see, we only have up to a total of 2 electrons in every orbital. Now we've said over here that also, the spin over here is going to be equal to basically either plus 1/2 or minus 1/2. In reality, it's but usually it's just simplified to get rid of the h bar and just go plus or minus 1/2. Now, when we're talking about plus or minus 1/2, what does that actually mean? So if you have an object with spin n, you need to rotate that object by 360 over n degrees to return to the same symmetry. So if you have an object here with spin 1, that's just going to be 360 degrees. Something with spin 2, that's going to be 180 degrees. Okay, so anyway, just to demonstrate a spin 1 object, so right here, this would basically be your spin 1 object. So here, again, we have a purple going up this way and that way. So if I just spin this by 90 degrees, that's not the same as what we started with. Now we're at 180. Nope, that's not the same. 270. Nope, not the same. 360. Yep, we're the same. So this would be a spin 1 object in this case. All right, and here would be a spin 2 object. So now notice I have my purple going back and forth like this, not up and to the right like I had before. So because this is now, if we rotate this, so remember we're going this way now. So if I do this by 90 degrees, nope, it looks different. But at 180, that looks exactly the same. So this would be a spin 2 object. Okay, now if we just extend this, and this would mean that a spin 1/2 object, so that would be 360 divided by 1/2, or 360 times 2, would be 720. Now, that is a bit of an oddball object because we don't have any normal things that if you rotate around by 720 degrees, returns. Now, obviously, if I rotate this around by 720 degrees, it's going to look exactly the same, but that doesn't count because it's the minimum number of rotations to get this here. So any natural object that you could probably think of that you rotate around by just 360 degrees is always going to return you to your original state. But there is an object that you probably have encountered back in grade school called a Mobius strip, right? So if you remember here, if you just take a regular strip of paper like so and bend it around, this is just a regular loop. We have an inside here, we have an outside, and the two are distinct. But now if I go here and give it a little half turn, this will actually form a Mobius strip because now this is going to just have one complete surface. So now here's my little Mobius strip, and of course what happens is if I start here on the top and I go around like this, keep going around, after I've gone around 360 degrees, I'm now on the bottom. And then if I keep on going here through another 360 degrees, so it goes around here, in there, comes out on this side, and boom, I'm at the top again. Okay, so with this little Mobius strip, I actually go around twice, in other words, my 720 degrees here, to get back to my original state. But if I only go around 360 degrees, I'm basically inverted in there. And now I'm not saying that electrons are Mobius stripped by any stretch of the imagination, so don't tell people I told you that. But essentially we're just trying to explain the weirdness of being a spin 1/2 object and trying to understand what actually goes on here. And there is some bit of truth to this, because if you look at the wave function, essentially if you rotate it around by 360 degrees, you wind up with the negative of the wave function you started with. You have to go around another 360 degrees to get your original wave function. And essentially what happens here is if you have your electron and you're starting out at this part, which would be your spin up, you go around 360 degrees, you end up with a spin down electron, you go around another 360 degrees, you wind back up with your spin up electron. Okay, so again, electrons aren't Mobius strips, but it's a weird concept and not something that we deal with in everyday life. And the other thing is over here, when we're talking with spin, this is actually referring to angular momentum of the particles here. So what we're going to go through here is, again, what spin is remember, this is an intrinsic property of elementary particles. It's an intrinsic angular momentum of the elementary particles. So what is angular momentum? And we also have discussed over here as well, the angular momentum quantum number as well. So this keeps turning up, so we should probably just define what we mean by angular momentum here. Okay, so L, that's just going to be your angular momentum. R, this is just going to be your distance from the center, basically your radius. and p, that's going to be your momentum. So the mass times your velocity. And these are vector quantities. Your angular momentum is a vector, your distance is going to be the vector, and your momentum is going to be a vector. And this right here is the cross product between the radius and the momentum, and that's where the whole little right-hand rule actually comes into play here. So how this is actually set up looks a little bit like this. So we can actually just look at, like the solar system as a nice little analogy here. So here we have our little analogy. We have here our sun, the Earth going around the sun, and the Earth is going to have a certain amount of angular momentum as it's going around the sun. So this is the distance between the Earth and the sun. This is the momentum of the Earth as it's moving around, so the mass times the velocity. And it's a little bit hard to draw that, but this is actually going to be right here. So here's my angular momentum, which would be my thumb. The radius right here would be basically my fingers, and then it's curling in the direction that this thing is actually going around. So this would be going this way. And the mv, of course, is in the plane of the solar system. The L sticks up and down from there. What basically happened was they said, okay, well, if the atoms are analogous to like little solar systems, well, this is the electron going around the proton, right? So this is analogous to that. And then what they started thinking was, well, maybe if we have the Earth going around the sun, which has a certain amount of angular momentum. We also know that the Earth is spinning, and that spinning also causes a little bit of angular momentum as well. So they said, well, maybe, just like the electron going around the proton, maybe the electron is also spinning. All right, and this is kind of where they came up with the original thing for spin, and why, historically it does have the name of spin. However, if you just kind of think about, here's your little electron and it is spinning around like this, that is not actually true, okay? Because if you actually work out the math and say, okay, well, if the electron is this size, obviously not this size, but a certain size, and to be spinning to give you an angular momentum corresponding to h bar over 2, it works out that the electron surface, that if you're dealing with a spherical ball like this, even under best case scenarios, is going to be spinning at several times the speed of light, which is a big problem because Einstein said that's a big no-no. The whole idea of the electron being a little spinning ball is completely wrong. It doesn't phase with reality. And again, the reason that the electron has spin, it's just a property of the particle. It's not actually the electron itself twirling around or anything like that. That is not what actually happens. Now, how they actually figured out that the electron has spin was by using the Stern-Gerlach experiment. Here's the Stern-Gerlach experiment. What they did was heat the silver in an oven to about 1000 degrees Celsius so they could have some silver atoms in the gas form. Of course, all this was done in vacuum. Those atoms were then collimated into a beam through some slits about 0.3 millimeters wide. The beam of silver atoms went through some specially shaped magnets, which were 3.5 centimeters long. As you'll notice, the north pole of the magnet is in a wedge shaped. The reason is you don't want a homogeneous magnetic field because the atoms wouldn't feel any force. What you need is a magnetic field gradient. In other words, the magnetic field is inhomogeneous and the strength changes as a function of distance. The magnetic field was about 0.1 Tesla and the gradient was about 10 Tesla per centimeter. And then depending if the spin of the electron is either up or down, the magnetic field gradient will either force the atoms up or down. And since the spin is quantized, the atoms will either go up or down by the same amount. Classically, if the spin was not quantized, you would see a broadening of the beam, but not two distinct lips. Here's an image of the plates which had the silver deposited on them. This was actually from a postcard which was sent to Niels Bohr in 1922. The message translated reads, "Attached is the experimental proof of direct quantization. We congratulate you on the confirmation of your theory." On the left is the beam without the magnet and is just a straight line because there's no force being felt either up or down. On the right is with the magnet and the beam has been separated into two distinct lips. This experiment was done in 1921 and 22, however they didn't know what was actually happening at the time. Interestingly, for orbital angular momentum, it was predicted that the beam would be split into an odd number of beams, 1, 3, 5, and so on. Remember the magnetic quantum number? It always has an odd number of suborbitals, so that's basically how the beams would split. However, at the time, there was no theory to predict an even number of beams, so this was, again, quite confusing. And since their experiments, this has also been done for copper atoms, gold atoms, sodium atoms, potassium, cesium, and hydrogen atoms as well. As a little interesting historical side note, Stern described how they were able to see such a weak deposit of silver. So after venting to release the vacuum, Gerlach removed the detector flange, but he could see no trace of the silver atom beam and handed the flange to me, which was Stern. With Gerlach looking over my shoulder as I peered closely at the plate, we were surprised to see gradually emerge the trace of the beam. Finally, we realized what had happened. At the time, I was the equivalent of an assistant professor. My salary was too low to afford good cigars, so I smoked bad cigars. These had a lot of sulfur in them, so my breath on the plate turned the silver into silver sulfide, which is jet black, so easily visible. It was like developing photographic film. And here is a commemorative plaque in Frankfurt, Germany. You can see the diagram of the experiment on top. Atomstrahl is atomic beam, Rinne translates as gutter, and Schneider is a cutting edge. So I'm guessing something is a little bit lost in the translation, but it must be referring to the atomic beam traveling through the space between the magnets. As you can see, the bottom one looks a little bit like a gutter, and the top magnet is wedge-shaped. Also, the dB/dz refers to the magnetic field gradient. B is the magnetic field, and z is the up-down distance. And here is a translation thanks to Google Translate. In February 1922, the fundamental discovery of the space quantization of the magnetic moments in atoms was in the Physikalischer Verein, Frankfurt am Main, by Otto von Stern and Walter Gerlach. In the Stern-Gerlach experiment resulted in major physical and technical developments of the 20th century, such as nuclear magnetic resonance method, atomic clock, or lasers. Otto Stern in 1943 would be awarded for this discovery the Nobel Prize. All right, so now that we know essentially a little bit of history behind, the discovery of spin and everything, we can combine all four of these quantum numbers that we were just looking at here. So the principal, the angular momentum, the magnetic, and the spin quantum numbers, these are basically the four variables that will describe the condition of the electron inside the atom. And the thing is, using this thing called the Pauli exclusion principle, every electron has to have a unique combination of these numbers. You cannot double these numbers up. Pauli said, in an atom there cannot be two or more equivalent electrons for which the values of all four quantum numbers coincide. If an electron exists in an atom for which all of these numbers have definite values, then this state is occupied. Okay, so that's the Pauli exclusion principle. So every electron has to have four unique quantum numbers. You cannot have two electrons with the exact same quantum numbers. Now, you can have 3 out of 4 the same, or 2 out of 4, or 1 out of 4 the same, but you cannot have all four exactly the same. And this is the whole reason why, when we were dealing with these, we could only have 2 electrons per orbital. Because remember, here we had my, let's just go down here. So here I had my n equals 3. Well, I could have, my angular momentum being 0. That could be 0. And then that could be, there's one possibility, but I can fit 2 electrons in there. So that would be my plus or minus a half, right? Down here, that's going to be 3, a 2, and then you could have any one of these 5 over here. And then, of course, for every one of these, you can fit 2 electrons in, either plus or minus a half. And that's why you have a total of 10 electrons. So that's why, these things fill up in this particular order, and why the whole periodic table has the shape that it actually has, right? So if you remember right here, the reason, these are my s orbitals over here, these are my p orbitals over here, here are my d's, there are my f's. This is why they have these certain amounts in there, because there are 3 p orbitals here, each one can take 2. That's why there's a total of 6 elements in this row. There are 5 d orbitals over here, each one can take 2. That's why there's 10 elements. The s orbitals, there's 1, it can take 2. That's why there's 2 elements. And down here, if you count them out, there's 7 possible orbitals. And they can take each 2 electrons. That's why there's 14 elements down here. So that's why the periodic table is arranged in that order there. Now the Pauli exclusion principle, while we usually just talk about it in terms of electron orbitals and everything, this also holds for protons and neutrons. So protons and neutrons have nuclear shells in them, and they have particularly stable isotopes compared to those around them. And they're attain essentially what could be analogous to noble gas configurations for nuclei, and these are actually called magic numbers. So there are certain nuclei which are much more stable than the nuclei around them. And we can also generalize this to a whole class of particles called fermions. So fermions have half integer spin, in other words, 1/2, 3/2, 5/2, and so on. So if you have one of these fermions with these half integer spin, this obeys Pauli. There's the other class, which is called bosons. So bosons have integer spin, and these do not obey Pauli. Now, the fermions are generally going to be matter particles, things like your electrons, your protons, your neutrons, and all that. Your bosons are generally going to be force carriers or force particles. So things like the Higgs boson has a spin of 0. The photon has a spin of 1. The gluon has a spin of 1. That's the thing which holds quarks together inside of protons and neutrons. The W plus, W minus, and Z0, those are also spin of +1. Those are what operate for the weak nuclear force. The graviton has a spin of 2, although it technically has not been actually found yet, but because it is attractive to everything, it winds up that it has to have a spin of 2 for the graviton. And these do not obey the Pauli exclusion principle. In other words, while the fermions, you cannot put a whole bunch of particles into the same orbitals because they would have the identical quantum numbers. Bosons, you can put all the same particles into the same quantum state, and there's absolutely no problem with that. Okay. So photons can of course form lasers. They have the same frequency, wavelength, phase, energy, and everything, and that's why they form lasers, because they all are nice and coherent light. You cannot do that with particles, right? You cannot make a actual particle laser. Now, with the Bose-Einstein condensate, which is, if you remember way back in August when we talked about this, that's if you cool matter down to extremely cold temperatures, just a tiny bit above absolute 0, you can actually get some of the fermions or some of the normal matter particles to actually start behaving like bosons, and you can actually get coherent states like with lasers. But other than that, photons, can form lasers. You cannot form lasers out of regular matter particles. Now, spin is also important from a technological standpoint and forms modern technology that is very important today. So you may have heard of these two things. So NMR, which is nuclear magnetic resonance, and MRI, which is magnetic resonance imaging. Now, they are essentially the same technology. NMR, if you go into an organic chemistry lab, you will pretty much find one of these. And the NMRs over here, when referring to the nuclear part of this, is referring to the proton spin. That's what the nuclear part is talking about. So what's taking is essentially the proton and applying a magnetic field, applying some radio waves, flipping the spin, and from there you can actually figure out your environment of your protons inside of your molecule. Now, when you're dealing with humans, of course, this is called the MRI, magnetic resonance imaging. Now, it's essentially the same technology, but they decided to call it MRI because the public is generally dumb, and you mention the word nuclear and they start freaking out. So it's really the same stuff, even though there is absolutely no radiation, at least high frequency ionizing radiation with magnetic resonance imaging. So there's, of the imaging techniques that you can have, MRI is probably about the most benign that you can actually get. Now, how this actually works is if we have a particle, or I should say here like a proton. So if we have no field, essentially the spin of my proton can either be up or down, and it's going to be essentially at the same energy level. So without an external field present, it can be either up or down. There's no way to tell which one it actually is. Now, if I were to put this over here into a magnetic field, there's going to be a splitting which goes on. So the magnetic field, or the spin of the proton, right? So the spin of this proton can either be what we call anti-parallel or parallel to the field. So right here, this is going to be my magnetic field. So this would be what we call parallel, and that'd be anti-parallel. Now, if we have the proton here, which is parallel to the magnetic field, it actually lowers it in energy a little bit. We have it anti-parallel to the magnetic field, it raises it up in energy a little bit. And between these two states over here, we have a change in energy. So essentially these two things are at different energies. Now what we can do is we can blast the person or your sample with radio waves, and it's going to go here and flip these spins over here and from the parallel state into the anti-parallel state. And now they're all going to be promoted, so you're going to have a large population up here. And then after you've blasted with radio waves, you essentially turn on your antenna, wait for the radio waves to be emitted as the stuff up here relaxes back down to the lower energy state. You record those radio waves, do some fancy math, you can actually figure out what the energy difference is, then you can figure out what the shifts are, determine how much water is in the system, how much shift actually goes on because of the molecule and everything. So you essentially can find out your local environment of the particles if you do this. So essentially, I mean, without getting way too complicated here, that's essentially where these the spin of the protons actually comes in to be very, very handy with that. Here we will look at the hydrogen-like atomic orbitals. So what are you looking at is a constant probability surface. In other words, the point where the probability of finding the electron outside that surface drops below a critical value. So we can't say we'll never find an electron outside this distance, but 99% of the time it will be inside the surface. So here are the s, p, d, f, and g orbitals. Now g would be for the L equals 4, which we didn't cover. However, no current elements have ground state electron configurations that high, so we're really not going to worry about it too much. The two colors represent the phases of the orbital. If you think of a sine wave, it has a part which is positive and a part which is negative. So that's the same thing being represented here. When you square the wave function, it becomes real and greater than or equal to 0. And there's no way to measure the phase of a wave function. However, if you have two wave functions interacting, such as two positive or two negative wave functions, those can constructively interfere and cause an increase in the probability density. And this is what we would call the formation of a bonding orbital. On the other hand, if you have a positive and a negative phase interact, then you would have destructive interference and an antibonding orbital would form. In that case, the atoms would be repelled from one another. So here on the top we have an s orbital. It's spherical and fairly boring. Next we have the three p orbitals, px, py, and pz, and they essentially just look like two balloons tied together. Next are the 5d orbitals. The middle one looks like a p orbital with a donut around its middle. But the other ones kind of look like butterflies. Next are the 7f orbitals. Again, the middle one looks like a p orbital with now two donuts, and the rest look like exploding butterflies or flowers. And then on the bottom, the 9g orbitals continue with basically the same pattern and getting more and more complex. Here are some things to pick up on. Notice the symmetry of the orbitals and the symmetry of the phases. The lobes on opposite sides of the p and f orbitals are of different phases. But for the opposite sides of the d and g orbitals, they are the same phase. Also, as you go down this chart, the number of lobes increases. And there's a certain beauty in the equations that as you increase your angular momentum, the number of lobes and also the phases change in a predictable manner. And you can probably guess what the 11 orbitals in the H level would actually look like. I'm not going to ask you to draw them out since that would be very, very messy. But I mean, you should be able to kind of get an idea of what they would actually look like. Now just to notice, all these images right here are just for the 1s, 2p, 3d, 4f, and 5g orbitals. Now as you go to higher energy levels, the wave function starts oscillating and adds more nodes as you go up in energy. So for the 3s orbitals, it is not just a bigger version of the 1s orbital, but it has additional nodes on the inside where the phase shifts from positive to negative and back to positive again. However, the probability does move outwards, so the odds of finding the electron at a greater distance do increase. Here is a more complete version of all the orbitals. So the white is your negative phase and the colors are the positive phases. As you can see, as you go down the periodic table, the Morse phase oscillations inside the orbitals actually occur. And as you go down each row, one more internal orbital is added. The blue and the white are the s orbitals, the yellow and white are the p orbitals, the red and white are the d orbitals, and the green and white are the f orbitals. Their position doesn't represent where the electrons in a particular element actually go, but it's more of an illustration as to what orbitals are being filled up in a particular area of the periodic table and what they actually look like. Okay, this has gotten to be ridiculously long, so I will stop this here.
I'm taking this loop off. Telling you, Teal, if we don't find a way out of this soon, I'm gonna lose it. Lose it. It means go crazy. Nuts. Insane. Bonzo. No longer in possession of one's faculties. 3 fries short of a Happy Meal. Wacko!